Okay, this is going to be the first of several videos on the concept of center of mass and how to locate the center of mass of an object. And usually it'll be some kind of a flat plate. So before we get into it, let's just take a quick look at what it would look like if you actually looked at some examples. So what we're going to look at is this. Now, it could be the object that you're looking at if it's a flat plate. It could be a regularly shaped flat plate like a rectangle like this, or it could be something irregular like this. Now, if it's a regularly shaped object, in a lot of cases, you really don't need any calculus. Suppose this, you had a flat plate and it looks like this, and you want to balance it on your finger. So the idea is, if it's in the shape of a rectangle, from geometry, I think you know if you come about halfway over and halfway up, and right about here, this would be the center of mass of that object. So if you were to balance that plate on your finger, it would balance right there. Now, it varies just a little bit. Let's take a look at this one. This one is also a rectangle. If we went halfway over and halfway up, it would be, say, about right here. But you can change things a little bit. Suppose we did this. Let's go in and we'll get rid of part of this. And let's put a little extension here. So suppose it went out like this, up like this, and over like this. So now we've changed the shape of it. Well, now it's not quite so easy, but you could probably guess if you look at it, it's going to take the center of mass and it's going to shift it from here, probably up to about right here. So if it had that little extension on it, and I tried to balance it now, the center of mass would be, say, located about right there. And finally, if it's an irregularly shaped object, center of mass, and again, just kind of eyeball things, stand back and say, well, I'm going to guess if I were trying to balance that on my finger, it would be about right here. Now again, if it's a regularly shaped object, you can actually get by without calculus and just using concepts of geometry and algebra come up with an answer. But if it's irregular like this, you're probably going to have to use concept of calculus with integrals to solve it. So anyway, the idea here is to try to find the x and y location of the center of mass of whatever this is. Now, in this case, if it looks like this, these are two-dimensional objects. They have length and width, but we're actually going to begin with what's called a one-dimensional system. So let's take a look and see what that's going to look like. Now, in a one-dimensional system, everything will just be strictly on the x-axis. So first of all, you will need some kind of a mass, and actually some terms for you. Let's go ahead and look at one of the terms we'll need first. A new term that some of you may or may not have run across before will be the concept of moment. So what moment is, moment's defined to be mass times distance. If you've had a physics class, you might be familiar with this. And it's similar to torque, where torque is defined to be force times distance, moment's defined to be mass times distance. So we will use moment to help us calculate the center of mass. First of all, you'll need this. If you've got a mass times a distance, so we need a mass, let's just go ahead and stick a mass on there. So if we had this, now suppose we had this, we had an 8 kilogram mass. Now, you can put this mass wherever you want to. Right now, it's located 2 units to the right on our little grid. If you wanted to, you could move it and put it over here at -3. You can put it wherever you want to. Now, what you can't do, though, is this. If it's a one-dimensional system, you can't move it off the x-axis. So if you try to put it up here, now it's got both an x distance and a y distance, so that would be a two-dimensional system. So in this first video, everything's going to be one-dimensional. So just to give this a place, let's suppose we started, and let's put it right here. So we'll put it 4 units to the right. So there's the mass. Now what we'd like to know is, what is the moment of this system right now? It just consists of one mass. So what the moment is, it's just mass times distance. So it will be this mass times the distance from the origin, which in this case would be 4. So I'll go over here, and actually I think I'll write it like this. If we wanted to calculate this, you would say that the moment about the origin would be equal to the mass, which is 8, and we'll assume that this is kilograms, so 8 kilograms, and the distance, let's suppose that that distance is 4 meters. So in this system, when you multiply that together, you would get 32 kilogram meters. And that's going to be the moment of the system about the origin. Now let's try a different one. This one had a positive torque. You could be negative. Let's go ahead and we'll get rid of our 8 kilogram mass. Let's suppose we had a 5 kilogram mass. Now this time, let's do this. Let's take our 5 kilogram mass and let's move it. Oh, suppose we moved it over to right here at -3. So now you've got a mass times a distance. And again, we'll calculate this new moment for the system that looks like this. So I want the moment. And it's going to be equal to, in this case, 5 kilograms. And this time it's a -3. So there's actually a sign associated with the distance. So if the distance is to the right, it's positive. If the distance is to the left, it's negative. So that's going to be a -15 kilogram meters. So on this first example, just keep in mind, if the mass is to the right, it's positive, the distance is positive, mass is to the left, it's negative. So you could have a positive moment or you could have a negative moment. Now what this was all just based on a single mass. Now suppose you decide to put 2 or more masses. In that case, you would have a system, and let's see what that's going to look like. Okay, now suppose we had this. We have an 8 kilogram mass, and we also have a 2 kilogram mass. Now the 8 kilogram mass is located out here 4 meters, and the 2 kilogram mass is located -3 meters to the left. And what I'd like to do on this is to find out where the center of mass of this system is. Let's first of all picture what that would actually look like. I think it helps if you picture this first. So let's go ahead and do this. You've got an 8 kilogram mass, and to actually connect these together, let's put a bar between the two of them. So I'm going to go from here over to here and actually draw, we'll just call it a black bar that goes right in here. So you've got something that looks like this. Now, if it helps you to picture what's going on, let's do this. Let's go ahead and get rid of the grid for a second. And temporarily, we'll get rid of the origin as well. And I just want to know, if I were going to balance this, now we'll assume here that the bar has no mass. All the mass is concentrated in the 2-point masses, 8 kilograms and 2 kilograms. So the question is, where would you put your finger if you wanted to balance this system on your finger? So I'll add a center of mass to this. And what we're going to do is this. We're going to move it around. And the idea is, if it was in the center, that probably wouldn't work because you've got the larger mass on this side, smaller mass on this side. So I think you can realize you probably would take it and move it this way somewhere. And you kind of make a guess. If you tried to balance it, and without any grid or anything, you wanted to balance it, I'm going to say it would probably balance somewhere about right there. Now, maybe a little bit to the right, maybe a little bit to the left. But I'm going to say roughly that is what the center of mass is. And in this problem, what we want to find out is, where is this? What point would you pick to balance the system out? So now with that, let's go ahead and turn the grid back on so we can see what's going on. And we'll put our origin back in there. So it looks like, so our guess is that it's going to be maybe somewhere right around in here. Now, to calculate the center of mass, there's actually a series of steps that work. So let's go ahead and put those steps on there. What will happen is this, and it will look like this. So I've got the total moment about the origin. Now, first of all, you can have individual moments of a single mass. The total moment about the origin is the sum of all of the individual moments. So what you've got is a mass 1 times a distance 1 plus a mass 2 times a distance 2. Then if there was a 3 times a distance 3 and so on. Then you'll have a second concept. The total mass of the system is just the mass of all the individual weights. And then finally, the center of mass of the system is defined to be the total moment of the system divided by the total mass of the system. It will give you a distance x bar, and what x bar is, it's this distance from the origin to the center of mass. So it'll tell you exactly how far you need to move to locate the center of mass. So the whole concept's actually pretty easy to work with. So let's go ahead and try this and see what it's going to look like. So in our problem, we'll kind of start with this one. We've got a mass 1. So the first mass is 2 kilograms, and the distance is a -3 meters. So we'll put that right here. So we've got the mass 1 is 2 kilograms, and we'll add the units later on, times a -3 meters. And we're going to add to that mass 2 times distance 2. Well, mass 2 is 8 kilograms, and its distance is 4 meters. So if you add those together, you get -6 plus 32, and that's going to give you 26. Now again, the units will be kilogram meters. And what this is the total moment about the origin. So you've got the moment of the system. Okay, the next thing you need is the total mass of the system. So the mass of the system would be equal to just the first mass plus the second mass, in this case, 2 plus 8, or the total mass of the system would be 10 kilograms. Now, the next thing you want to know, you want to find x bar. And again, what x bar is the distance from the origin to the center of mass. It'll tell you where to locate this, because right now you're not sure where it is. So again, easy to computate. The total moment was 26 kilogram meters. So 26 kilogram meters divided by total mass, which is 10 kilograms. So kilograms. Again, when you divide these, the kilograms will cancel out, and that's going to leave you with 2.6 meters. So what 2.6 meters is, and actually let's go up on our graph and do it. I'll move our center of mass over. So 2.6, and we'll do it right here. We're sitting right here. 2.6 is about right here. There's 3, so 2.6 is going to be about right there. So what that is, this distance from here to here is 2.6, and it tells you exactly where the center of mass of this system is. So again, fairly easy system to work with. Now let's do this. Let's add one more thing just to give it a little variety. What this is an unbalanced system. So let's see what a balanced system would look like, just to try a different type of problem. So I'm going to go ahead and turn this work off. And let's do this. Let's get rid of our 2 kilogram mass and replace it with an 8 kilogram mass. Now let's suppose this. We've got an 8 kilograms, suppose it's the same distance. So 8 kilograms, 4 meters to the left, and 8 kilograms, 4 meters to the right. If you were to try to find the center mass of the system, you would probably think, and think correctly, that it should be balanced. This center of mass should be right here in the center, which means that x bar should be 0. But let's go ahead and try that and just see what it looks like. So we'll go up to here, and we'll rework the same problem. So now we've got this. The first one is 8 kilograms times minus 4. So 8 times minus 4. And you're going to add to that this one, which is 8 times a positive 4. And what that's going to give you is a negative 32 plus 32, which would be equal to 0. And again, the units will be kilogram meters. So the net torque on the system is 0. Now the mass is still, in this case, it's going to be 8 plus 8, which would be 16 kilograms. So the system still has some mass. So now where is the center of mass of this thing? Well, again, total moment is 0 kilogram meters divided by 16 kilogram meters. And kilograms cancel out. 0 divided by 16 would be 0 meters. So what that means, if x bar represents the distance from the origin to the center of mass, then in this problem, now remember in the last problem it was 2.6, it was over about right here. But if the distance is 0, that just means that the center of mass is located exactly the same place as the center of the origin, which is what you were expecting since you had an equal and a balance. So this would be a balanced system. Okay, now that was 2 masses. Let's suppose we had one more problem. Let's suppose you add some additional masses to this thing. So on this one, we've got something that looks like this. Now in this case, we've got an 8 kilogram mass, we've got a 5 kilogram mass, a 3 kilogram mass, and a 2 kilogram mass. And we're going to use the same 3 steps to solve this. So first of all, find the total moment, find the total mass, and then the center of mass will be the total moment divided by the total mass. But just let's make it a little bit more extreme before we get started. So let's do this. Let's take our 5 kilogram mass and let's move it to, say out here. We'll make it heavily biased to this side. And then finally, let's also do this. Let's take the 3 kilogram mass, and we haven't done one like this, so let's put the 3 kilogram mass right here at the origin. So suppose the system looks like this. Now what you'd like to know is where are you going to balance this thing? So again, we will, let's turn off the grid. Sometimes it helps if you try to picture what's going on. The grid is confusing. So let's just turn the grid off and look at this. And suppose that we had this center of mass. So now the question is, where should I put this center of mass to balance this? And it's kind of a guess. The heavy masses are on this side. The light masses are on this side. So your guess is probably about as good as mine. I'm going to guess that it would balance somewhere maybe about right there. Let's just leave it right there. We'll solve the problem and see how close we came to hitting the final answer. So just if you were just doing it without any math or any kind of a grid, you would make a guess that the center of mass would be located somewhere about right there. So let's go ahead and turn the grid back on, solve the problem, and see what we come up with. Okay, now we're going to use exactly the same steps that we did last time. Each mass times its distance from the origin. So in this case, we'll have this. The moment about the origin. So the moment about the origin will be the first mass is 8 kilograms times -4. So you'll have 8 times a -4. And you're going to add to that the second one, which is 5 times a -3. So 5 kilograms times a -3. Then the next one, 3 kilograms. Now, it's located at the origin, so its distance is going to be 0. So you've got 3 kilograms, but at a distance of 0. So in effect, that doesn't add any moment at all. Then finally, you've got plus. Now, the last one is 2 kilograms, and it's out at a distance of 3 meters. So the individual moments, this one would be minus 32 kilogram meters. This one would be minus 15 kilogram meters. This one would be 0. And this one would be 6. So if you add all those together, you would get negative 41 kilogram meters. So what this is the moment about the origin, the total moment of the system. Okay, the total mass of the system is just add each one of the masses. So 8 plus 5 plus 3 plus 2. So 8 plus 5 plus 3 plus 2. And that's going to give you, let's see, 5, 10, that's going to give you 18 kilograms. So we've got the total mass of the system is going to be 18 kilograms. Okay, so the total moment of the system was negative 41 kilogram meters, and you're dividing that by 18 kilograms. Okay, now again, the kilograms cancel out, and that's going to give you about a negative 2.8. So negative 2.28, actually, meters. So again, what this is x bar, and that's the distance between the origin and the center of mass. So let's see where that actually puts our thing. We'll go back to our center of mass and move it to negative 2.28. And actually, we were pretty close on this. If you look at this, there's negative 2, here's negative 2.5, so negative 2.8 would be about right there. So our guess was actually pretty good. So the distance from here to here is negative 2.28. So again, in summary, when you work these out, really it's kind of a 3-step process as you go through this. Let's go ahead and we'll just put steps on there. The first step is to go ahead and find the total moment of the system. So this would be step 1. So step 1 is just find each individual mass times its distance from the origin, and that's going to give you the total moment of the whole system. Then you move to step 2. Step 2 is find the mass of the system, so add up all the masses, that'll give you the total mass of the system. And then finally, step 3, to locate the distance of the center of mass from the origin, and that's what this is right here. That's going to be this distance from here to here this is going to be x bar. So divide the total moment by the total mass. That'll give you the distance to move from the origin. Again, if it's negative, move to the left. If it's positive, move to the right. And you'll find the location of the center of mass, which in this case was negative 2.28 meters. So anyway, that's a sample. What this is a one-dimensional system. Now, what we'll look at the next video, and let's just kind of play around with this just a little bit. In the next video, we'll say, suppose we did this. Suppose we took this mass and moved it up here. Suppose we took this mass and moved it down here. Let's take this one and move it here. Let's move it over here. And finally take this mass and move it here. Well, now what you've got is a two-dimensional system. So the question is, where is the center of mass of this system? And that's what we'll look at in the next video, is how to find the center of mass of a two-dimensional system.